Okay, welcome back. So we're on to P13 now, which is electromagnetic induction. Okay, so remember in the last lesson we looked at the motor effect, which was essentially movement being caused when you had current passing through a magnetic field. Okay, in this in electromagnetic induction, we've got the opposite occurring. Okay, we have movement of a wire in the presence of a magnetic field, creating current and voltage. Okay, so let's look at these examples here. So an electric current can be generated by using both of these methods. Okay, so here we've got a coil of wire. Remember we said that's a solenoid in the previous video. What happens when we move the magnet to the right? Well, essentially we're going to get a voltage and a current subsequently being induced. Okay, same thing when we move this wire. Notice the arrows pointing upwards, so we're literally moving it upwards. When that occurs, we're going to get a current being produced, and this ammeter is gonna take a reading. Okay, so what is actually happening? Well, in both cases, magnetic field lines and the wire are cutting through each other. Okay, so essentially the wire is interacting with the magnetic field lines from the magnet, which essentially interact with one another. We say they cut through each other, and that generates an electric current, okay, and a voltage. A larger current or voltage will be generated when more field lines are cut every second. Okay, so if we've got a faster movement, or if we've got a larger area of the wire, or a larger amount, so a longer length of the wire being present in that magnetic field, we're going to generate a lot more current or voltage. Okay, specifically, what do we mean by the field lines being cut? Well, if we look at this wire, it is 90 degrees, okay, to the direction of travel of these magnetic field lines. So in the previous video, we talked about the magnetic field lines going from the North Pole to the South Pole. Okay, so if you imagine they're going in this direction here, and that is literally 90 degrees to this wire here. If we rotated this wire so that they were parallel, so it was parallel to these magnetic field lines, doesn't matter how quickly you move that wire through, okay, you will not be cutting the magnetic field lines. Okay, so when we talk about the magnetic field lines being cut, it means the actual wire or coil of wire is passing 90 degrees with respect to the magnetic field lines. Okay, so it's cutting the magnetic field lines, which means no current or voltage will be generated when no field lines are cut. Okay, so if obviously if we've got no movement when the wire is 90 degrees to the field lines, and also if it was parallel to the magnetic field lines, we would get no field cutting. Okay. So we talked about how do we increase the size of this induced voltage or current. Well, essentially we can have a larger magnet. Okay, so just increase the size of the magnet, that gives us a larger magnetic field. We can move the wire a lot faster, really quickly, or we can just have a longer length of wire. Okay, so have more coils of the wire. How do we reverse the direction of the voltage or current that's produced or induced? Well, we just simply move the magnet or wire in the opposite direction. Okay, so now let's look at two devices that make use of this wonderful effect of electromagnetic induction. Okay, so they are alternators and dynamos. So let's start off with alternators. So if we look at this diagram here, okay, so what is the purpose of the slip rings? Well, first of all, they are rings, so they are circular, and the motion of the coil is also going to be a rotational a clockwise motion, as we see from this arrow here. Okay, so somebody is obviously twirling this coil around, or could be connected up to a turbine in a power station. But essentially what's going to happen, okay, we want a smooth rotational movement, and that's the purpose of these slip rings. Okay, now let's look at this in a bit more detail. So notice we've got two connectors here. Now at one point and our coil of wire has got two lengths, okay? So here we've got a shorter length and then a longer length, okay? So at the moment, this longer length is connected to this side of this slip ring, okay? And it's not connected to this connector. Whereas as this shorter end of on this side of the coil is connected to this side of this ring, and it is going to be connected to this connector, which means at this point in time we're going to get current flowing through this wire and through our circuit like so. Okay, so we're going to get current flowing in one direction. So we can imagine, yes, this does say potential difference or voltage, but we're going to get current moving in the positive direction. Now, as it rotates, now obviously you've got to imagine this. Okay, as it rotates, this wire, this side of the wire is going to end up here, which means this longer end is now going to reach this slip ring. Okay, pause the video just to make sure you're comfortable with that. But essentially, this is going to go all the way around to the top there, and then downwards, and it's going to reach this connector. Okay, that means we're going to current flowing through this wire, okay, around like this, and it's going to flow in the opposite direction, which means we're going to get current or voltage also in the negative direction. And this process continues. Okay, so again, when this long end of the wire is located here, this short end is located on the other side, and obviously when we continue to rotate it, again we come back to where we started off with. Okay, and we get this alternating current or alternating voltage being produced. Okay, so we've mentioned that each time this coil rotates, the shorter end of the wire and the longer end of the wire are going to switch positions with these respective connectors here. Okay, now that means every 0.2 seconds we're going to get a shape like this. Now, why is there a peak? Well, the peak occurs when the this end of the wire is right in the middle of the magnetic field lines, because when it passes downwards, notice there's less of it cutting the magnetic field lines, okay? And the same when it's at the top here, okay, there's a bit of horizontal motion, okay, or parallel motion, which means that you actually get less magnetic field lines being cut, whereas when it is rotating around this way, okay, the coil is actually cutting a lot more magnetic field lines, which means we get a peak voltage or a peak current. The same thing happens when we have this end of the coil cutting through the magnetic fields as it rotates this way. Okay, so at the top, again, it cuts through the magnetic field lines less. Okay, so we've got a small amount of voltage. However, when it comes down here, we get a peak voltage, and then when it leaves that position, okay, it's got some horizontal motion from the right to the left now, which means it cuts less magnetic field lines, and you get zero voltage being produced when the coil is at the bottom here and at the top there. Okay, and the last point to remember with alternators is they give out alternating current, or AC, and you can remember that by their name, alternators, alternating current. Okay, so let's look at the next device that utilizes electromagnetic induction, and they are the dynamos. Okay, so one particular point of the device I want you to look at is the split ring commutator here. Now, notice there is a gap, okay, between the rings, and that's why it's called a split ring, okay, because it's split in the middle, and that is to ensure that we do not get a spark or a short circuit from the current being generated from these two wires going across these rings. Okay, let's now look at this coil. Okay, so this section of the coil, okay, as it rotates upwards, when it reaches the top, that gap, okay, on either side of the split ring is going to be present. It's going to be present at both connectors, which means for a split second we're going to have no current being generated, okay? And in fact, that current can go nowhere for a split second. Now that means that the rotational movement, obviously by the turbine or a person's hand, is still going to continue, and then as it does, the top of the wire here is then going to continue to cut the magnetic field line, magnetic field lines, and it cuts more, remember, when it's at this position here, which explains why we have these peaks, and as it goes down again, the amount of magnetic field lines it cuts reduces, okay, which explains the smaller amount of potential difference of voltage down here. Now, what's really interesting is each time this coil rotates, okay, these connectors actually change as well, which means the current will always be moving in one direction, okay? So as this rotates upwards and it goes downwards, the current, due to Fleming's left-hand rule, okay, is always going to be coming outwards in this direction, okay? This device produces direct current. Now, how do we know that? Well, the magnetic field lines are going from north to south, that's staying constant, and the motion on this side of the axle is always a downwards motion, okay, or a rotational clockwise motion. Now, that rotational clockwise downwards motion continues to be the case, but all that's changing is this section here. But the beauty of the split ring commutator is that it ensures that the current that always comes out from the wire in this direction is always going to go outwards through the ammeter like so, okay? So we get direct current being produced and no negative current or no current produced in the opposite direction. Okay, and finally, again, they ask us to sketch what a graph would look like if the coil turned every 0.2 seconds. Well, every 0.2 seconds are sections of the coil, the wires are going to switch, which means we will get this pattern every 0.2 seconds. Okay, so we get the peak voltage when one side of the wire of the coil is in this region here, because that's when it's cutting the most magnetic field lines, and it's the least when it is at the top and bottom, okay, which explains the zero voltages here, okay.